conservative. See if it's conservative, do derivative of the first thing with respect to y, product rule. Derivative of the second thing with respect to x, another product rule. So this is the derivative of the first thing with respect to y. Pretty easy product rule. 2y, that's the derivative of y squared times e to the xy. And then xy squared because of the chain rule. So the derivative of e to the y is e to the y, but there's an x up there. So chain rule, throw that x over there. So xy squared e to the xy. So there's the derivative of this thing with respect to y. Then we'll do the derivative of this with respect to x. So I did that right here. Another product rule, a little bit annoying. I don't know what I did over here, but I got the same thing. What did I do? Oh, I know. Okay, so the derivative, I used this as the first thing. This is the second thing. So the derivative of that first thing with respect to x is just y. Because the derivative of 1 is 0, and the derivative of xy, x times a constant, is just y. And then I left that alone. Then I wrote that down, and then wrote down the derivative of this with respect to x using the chain rule, so you get this extra y here. Then simplified, and if you combine like terms, then it ends up being the same thing, and there's happiness and joy. So wherever it is there, yeah. So you have 2y, so there's one of them here, one of them here. So 2y e to the xy, just like over there, and xy squared. So then we're happy until we have to do the antiderivative because we're going to have to use integration by parts. But we can overcome this, can't we? Actually, the integral with respect to x is not hard at all. In fact, I did it in one step. So that's so just to review, after you've done your derivatives and you've checked to see that they're the same, the next step is to do the integrals of each of these, and then we combine them with this sort of a union-like thing where we make sure that all the little pieces are accounted for. So we're going to integrate the first part. This is the x coordinate, if you will. That thing, we're going to integrate that with respect to x. So that was easy because there's only one x there. It's here. You could use substitution. I just did it in my head, but the substitution would be that u is equal to xy. Yeah, u is equal to xy. Du is y dx. So you take one of these y's, smash it up here against this dx. It becomes du. Integral of e to the u is e to the u. You're left with one of the y's. Here's e to the u. So anyway, that makes sense. The second part I kind of did really quickly here, but I checked to see that it was the same, and it was the same. But let's go over it a little bit slower since this one is a little bit harder because it's going to require integration by parts. So let me just duplicate this and pull it down out of the way of all of my work. Yeah, there's my answer. Let's see, is there room here? Sure. Okay, so here's the thing we're doing. Let me separate this. So I'll do it slower now. I just wanted to make sure that I had the right answer before I started mouthing off to you guys. So the first thing I'm going to do is I'm going to expand. So xy e to the xy. We're doing with respect to y now. So this first bit is very similar to the bit that we had above with the integration with respect to x. So that's easy enough. That's going to be 1 over x e to the xy. So that's that piece. This piece is a little bit harder, so we're going to have to take a break or pause what we're doing here and do integration by parts. So I will do that maybe over here in this blank space. So we're going to do the integral of xy e to the xy with respect to y. Bear in mind, x is constant with respect to y. So x, we don't care about x, we just care about y. So I'm going to use u is equal to xy, and dv is equal to e to the xy dy. Now bear in mind, you could have moved this x outside the integral if you wanted to, and it's totally legal because that's an integral with respect to y, so you can move that x out. Anyway, let's go ahead, pound through the derivative of xy with respect to y, because this is all y. X is just, it's a throwaway, it's a constant. So the derivative of xy is just x with respect to y. I guess I should have a dy there. The derivative of, the antiderivative of this thing, we've done it already. We did it right here. So down at the bottom. So that's going to equal v is 1 over x e to the xy. And let's combine this. You have the integral of u dv is equal to the integral of v du. I'm sorry, uv minus the integral of v du. I got ahead of myself. Let's just finish this up. I know we're all excited about going and gorging ourselves with turkey. So let's just get through today, and then we can do that. So there's u times v minus the integral of v times du. So there it is, carefully written out. So let's go ahead and simplify things as much as possible. Of course, the x's are going to cancel here, so you have y e to the xy, and then this thing becomes just the integral of e to the xy dy, which we've done already. It's down there. So this will be the final answer. I'll do it in purple. This thing becomes y e to the xy, that's this one, minus this integral, which we've done a couple times now, so hopefully it's familiar, 1 over x e to the xy. Whew. Now you can see some things cancel, and we're going to be left with just this, y e to the xy. Almost done. So, done all my work. Now all I have to do is compare this to what I had above. Where is it? There it is. Compare this to this. And remember, we're just going to grab components like everything. We need to make sure everything is accounted for. So I need, in my function, I need to have y e to the xy. And when I put that there, that's going to be checked off. And then this also gets checked off. And then, oh, there's nothing else to, and so that's it. So there's my answer there. Is f of xy is y e to the xy. A little bit more challenging than some of the others because of the integration by parts. I know that that's not your favorite, but it's good practice, I think. So, well, was there anything else from this? Or does that, first of all, let's deal with 5. 5, we happy with 5? As happy as we can be, right? I know, you're not really happy. Okay, what else do we need to look at, if anything, from this? Yeah, what do you think, Cooper?
Can you do number 13 with the XY?
Yes. So this is so the first bit we were just dealing with finding the function, and then number, is it 15? Did you say?
Yep.
Yeah. So this one, I think we actually have to compute a line integral, don't we? Yes. So this brings it all together. So we're hoping that this is a conservative vector field, which I'm assuming that it is, since it's, let's see, it says find the function. So I think we can imply from part A that this is a conservative vector field, because if it wasn't, then you wouldn't be able to find such a function. Okay, so let's go ahead and do this one. And then, of course, the line segment. We know how to parameterize that now because we've done it so many times. So that should be easy. Give me a sec. I'd just like to move this problem down to where I have more room. Here we are. Find the line and then paste it in there. Okay, so first things first, we need to find our function that this is a gradient for. So bear in mind that I know there's three components, but you know what those components are. You know that this is the derivative of f with respect to x. You know that this, if this is a gradient vector field, you know that this is the derivative of f with respect to y, and similarly, this is the derivative of f with respect to z. So just like when you had 2 components, 3, you could throw in 4 if you want, but you're going to have the same deal that you have the derivative with respect to x, y, and z. By the way, if I wanted to check to see if this was conservative, it's going to be a big pain, because I would have to do the derivative of this with respect to y and then z, this thing with respect to x and then z, and this thing I do the derivative with respect to x and y. So if you were curious, how would we check to see if this is conservative? That's the way you would do it. But fortunately for us, we're not asked to do that. Okay, so bearing that in mind, I'm going to do the integral of the first piece with respect to x, and that's easy enough, x, y, z. I'll do the integral of the second piece with respect to y. That's also easy. And I'll do the integral of the third piece with respect to z. And that I get x, y, z plus z squared. So there's the three components. So check that, make sure that that makes sense, what I just did. I'll pause and see if you have any complaints, especially from Cooper, because you're the one that wants to know. Some other people don't care. So I appreciate your inquisitiveness. Okay, so once we're happy with that, we're going to combine all these, sort of like a union. So that's going to be my f. F is going to be x, y, z. And once I have that x, y, z written down, I'm like, okay, that's good, that's good, that's good. I still need a z squared, so I'll put that there. Now that one's okay. And I think I've got all the pieces that I need. I've put them together, and I've got my, my f. So that's going to be f. Next thing that you're going to do is you're going to parameterize this line. And I don't care how you do it, but I do it the easy way. So I'm going to write it like this, x, y, and z. And I put the starting point here. And then I add to this the difference between the two. So this will be 3t. This will be 6t. And this will be 5t. I think I got that right. And of course, if you do it this way, then your integral will just go from 0 to 1. So that's another nice thing about doing it like that. So far so good? Cooper, you're good? You're happy? He's happy. That's all I can ask for is get some joy here. Okay. Especially since some people skipped town early, apparently. So let's set up this integral. So now the line integral, hold on a minute. It's, oh, sorry. I have to deal with the whole thing, don't I? So I have to do f of r. So this here essentially is r. All of that stuff, that's r. Whoa, not an f. Get rid of the f. It's r. R of t is this stuff. Okay, so bear with me for just a minute because this is going to be a bit tedious. So we have y times z. That'll be 6t times negative 2 plus 5t I plus x times z. Oh, wait a minute. Duh. Sorry, I forgot. We're in the fundamental theorem of calculus. We don't even need this. We don't care. Don't care. Okay, yeah, someone, yeah, save me from myself. Once you have this, you don't care about the curve. This curve, it could be the line segment, it could be a curly Q, it could be anything, a little spiral. You can go whatever path you want. As long as this thing is conservative, we don't care. So all I need to do is I do f of 4, 6, 3, yes, thank you, minus f of 1, 0, negative 2. So plug and chug, you're all done. So what's this? 4 times 6 times 3 is 72, plus z squared, that's 9. And then subtract off 1 times 0 times negative 2 is 0, plus 4. So that's going to be like that. 72 plus 9 is 81, minus 4 is 77. Is that the right answer? I hope. All right, great. We got 77. We're happy. Yeah. So this was all extra work. This was me being dumb. Don't do this. Don't be like me. Just do this. Look, it was so short, super short. So that's the beauty of the fundamental theorem of calculus for line integrals, is once you have a conservative vector field, doesn't matter what path, just beginning minus end, or end minus beginning. Whew. That do it for you, Cooper? Thanks. And you knew when I started doing this nonsense over here. You're like, why is he letting him rail on? It's fine. Okay, well, I was trying to help you. Okay, so anything else that we need to clarify? So you could do this. I only have 2 components on this, not 3 on here. Let me just take a peek and make sure it's easy. Ah, yes, it's super easy. Okay, I hope. And we'll find out. Yeah, let's give it a go. Let's try this quiz out. See how we do. Here we are. 1, 2, 3, 4. Why not? Here's 2. There's probably only 3 there. Here's 1 more. Here's a few. Here's a couple more. There's enough here so that I know he wants it. Oh, you got extras. Great. I'll take one. Yeah, it doesn't matter. Yeah, I'll take one. You got extras. We need an extra? Anyone else need an extra? You've got extras. Why am I making so many? They're printing more than I need. I'll come back for the homework. cancel. Switch. Okay, verify. I see. You're going to do the line until the old fashioned one. A couple more coming in. All right, try to finish things up here in the next minute or so. You're all done ruminating. Very, very nice. Okay, beautiful. If it didn't change, it's very nice. I'm just worried. Don't think about it too much. If they're going to change something. All right, got it. Oh, you got this one. Hey. I don't know if that's right or not. I'll have to check on it. You could check on that. Let's see. Oh yeah, actually I know that it's not that decimal. That's good. Yeah. Oh yeah. I think I'll have it. Okay. Oh no. I can tell this here. I think it's right. So you think it's wrong? Oh, it's because you're going to make me do the math? You don't know this cosine of pi over t? It's okay.
Hilarious.
Yeah, that's fine. You can do it. You got it good. Excellent. Well done. Let's see. Yeah, I think. All right, let's see what we did. Do I have any more over here? Oh, you've got one here. I have over here. Sorry, I didn't notice. Oh, okay. Sad. Okay, let's see what I did. Let's see. Here we go. So I didn't show my work, but I can show my work if I need to. So here's the f of xy. Let's just double check though. The derivative of this with respect to x is this. You can check. And the derivative of this with respect to y is this. So I could have written down my work. My work would be do the antiderivative of this with respect to x. I get x squared plus xy. Antiderivative of that with respect to y, xy minus y squared. So there's my function. And then the main thing, I guess I was getting a little crazy here, but the main thing would be to figure out the start and end points. And so the start point happens to be 2, 0. If you plug 0 into all of this mess, you get 2, 0. So that may have been, I was a little bit maybe ridiculous there. But yeah, because the reason is tangent of 0 is 0, sine of 0 is 0, cosine of negative pi over 2 is 0. So it's all zeros. And then the end point, tangent of pi is 0, sine of 4 pi is 0, so that's all just 2. This will be pi plus cosine of 6 pi minus pi over 2. I don't know what that is, but it's a right angle, so the cosine is 0. So the end is going to be 2 and pi. Then you just plug them in, and you get, so there's f of 2 pi. It's right there. F of 2, 0, and subtract, and you're all done. So Subtract the top from the bottom. So yeah, most of you got this. Some of you didn't, or maybe you chose not to evaluate the cosine of pi over 2, and you still got it right because you wrote it down. So nice done. Nicely done. Okay, let me find my, hold on a sec. There it is. No, back to Wonka. We're not doing Wonka. That was the freshman. And some of you did Wonka, didn't you? So I don't want to discuss it anymore. Here we go. Okay, here's what we're doing. Okay. All right, so first things first. I got an email this morning. You probably got it as well, but everyone ignores that email. It's the one that says it's the announcements, you know, the announcements email that you don't read. But I thought I should just point out to you just one thing that was on that email, and that is that if you have 3 or more finals scheduled for a particular day, you can petition to have one of them moved. The problem is that you have to submit that petition by next Monday. So that's why I thought I should bring this to your attention, just in case. This is the final exam schedule. So you can see our final is right here. And I will give you more details about that next week. So I think I told you that it's a take-home final, and then you have to come and submit it between certain hours at my home. And then if you want bacon, you can have bacon, but you don't have to have bacon if you don't want it. If you're a vegan, you can just have fruit. But anyway, so that's us. I don't think that we should count as a final if you, I mean, in terms of 3 in a day. So if you have 2 more that day, but if you did. So here's why I bring this to your attention, is because if you happen to have 3 finals, for example, on this day, because what is this? This is physics, this is statics, and this is fluid dynamics. So you have all 3 of those on that day. I don't know if those were when those are, but if that was when those were, you could petition to have one of those moved to another day. Or you could just suck it up and do 3 finals in a day, you know, whatever. So it's up to you. But I wanted you to know, because the email said that you have to request this before or by Monday. Monday is the last day. So you can think about it over the weekend. But there it is if you need to. So you know where your finals are now. Can you see it all? Good. You can always go look at the recording and pause the recording. This also is available on the portal, but it's hidden in a it's hard for me to find every time I look for it. So I just download it at the beginning of the semester and hope they don't change it. So I'm pretty sure that they don't. They usually email us if they change it. Okay, so everyone's seen that. Good. Okay, we've done the quiz. On to Green's theorem. Okay, so we're just gonna, here's the deal for today. I thought that no one wants to do homework over the break, so I thought what we could do is just introduce Green's theorem today. I will show you the homework you've probably seen it, it's online. There's some very important things you should be doing over the break, but it doesn't involve calculus. And then we'll finish Green's theorem on Monday, and we will have the homework for Green's theorem due on Tuesday. So Green's theorem, what is Green's theorem? So it seems like mathematicians are, what we do is we take a theorem. Let me give you an example of this. You know the Pythagorean theorem? Well, I'm not going to teach you this now, so you can just sit back and close your eyes if you prefer. But the Pythagorean theorem is this. It's about right triangles, and it says that a squared plus b squared equals c squared, plus b squared equals c squared. And this is only true if you have a right triangle, right? And so this feels awfully discriminatory, because most triangles are not right triangles. And so if you have a triangle that's not a right triangle, what do? You can't use the Pythagorean theorem. That's sad, isn't it? Well, fortunately for us, there is another theorem that works for non-right triangles. So if this is A, B, and C, and you have some angle here that's not a right angle, then there's this theorem that looks awfully like the Pythagorean theorem. Specifically, it says a squared plus b squared is equal to c squared. Well, I've left a little gap there because there's a correction factor, isn't there? This is minus 2ab cosine of theta. So this is the correction for the fact that that's not a right triangle. We have a similar situation here with Green's theorem. It feels like it's kind of like, you know, it would be nice if all vector fields would be conservative, right? But unfortunately, not everyone is conservative, right? So we have to deal with all the liberals, or I'm sorry, all of the non-conservative vector fields. We have to deal with them, and that's what Green's theorem does. It's a way of simplifying doing line integrals whenever you have a vector field that's not conservative. So first of all, before we get to Green's theorem, we need to learn about this thing called simply connected regions. A simply connected region is just a region that has no holes or chunks. What in the world do I mean by a hole or a chunk? Well, here is a simply connected region. It's a nice blob. See, that's a simply connected region. It's just like one blob like that. Here's another one. I should have separated these with lines. Here, I'll just do my best because some others are going to come and appear. So this is, we'll call that A. We'll call this B. There we go. And then I'll have to extend my line. That's also simply connected. If you take that one separate from A, if you say that your region is those two, like the union of them, no longer simply connected because it's like two islands that are separated, not connected. But if you take this one individually, that one is simply connected. We've got a bunch of other silly diagrams. This is simply connected here. So we'll call that one C. Those are all simply connected. They're beautiful, aren't they? And even though that one is kind of weird, it's got little spikes going out, it is still simply connected. This is not simply connected. So this one, unfortunately, you have these points where the region comes to a point. So that's not simply connected. We can fix this region, but for now, we're not going to be considering regions like this. So that's what I mean by a chunk. It's chunked up, kind of weird. So that's no. Here, I'll zoom back out. I'll continue drawing little lines. This one, D, is no. So here, yes, we like yeses. A, B, and C are all yeses. No is D. Okay, what else? Okay, this one, whoops. Oh well, I'll erase my line. Okay, so that one has a hole in the middle of it. So that's not simply connected. Once again, it is possible, we'll call that one E. E is not simply connected because it's got a hole in the middle. We could deal with this. It's possible to apply Green's theorem to this, but we would have to be careful. It's possible, though, to deal with that. Okay, next one. What about that? Definitely not simply connected. It's actually two separate regions. You've got a gap in between them. So that's a no. We'll call that one F. And then the last one, no. Even though we are happy about that one, it is a no. So here I'll draw lines. A, F, G. G is not simply connected because it's got a bunch of holes in it. Once again, we could correct Green's theorem. We might do that next week, but for now, we're just going to deal with the basics. So what does Green's theorem do? Well, Green's theorem allows us to compute line integrals quickly in vector fields that are not conservative. So the way that we're going to do this is we're going to apply this rule, this theorem, and that is that if you have a line integral through a vector field, as long as this line integral is the boundary of a simply connected region. So they've got some extra restrictions, and we can fix, it's possible to deal with some of these issues. In the future, we can correct for some other things. You might say we're still being pretty restrictive, but if your curve happens to be the boundary of a simply connected region, then this is Green's theorem here. So, and we have to be very specific that C is traced around the positive, the counterclockwise direction. You know how mathematicians are. We think of this direction as being positive for angle measurement. You're going around, you're like, well, that's not the way a clock moves. Well, yeah, well, mathematicians didn't invent clocks. Well, actually, we did, didn't we? Well, I don't know why we go this way for clocks or the other way. But angles are always measured counterclockwise. So the curve is traced in the counterclockwise direction. So what we're going to do is we are going to do a couple of examples and then call it a day. Actually, we're going to do one example, and that's this example. So this particular symbol here with the little circle around it, that just means that we're doing a line integral around a region. So the region happens to be a triangle with vertices at 0, 0, 1, 0, and 1, 2. Okay, so let us do this. So we're going to do this directly, and then after we do it directly, we're going to do it using Green's theorem. So give me a sec. And this is our only task today. once we get done with this task, we will be done for the day, and we will all go away happy. Okay, paste this in here. Okay, so first things first, let me sketch this region. The region, unfortunately, it's 3 line segments. So we have this triangle. By the way, that circle means that we're going in the counterclockwise direction around our curve. Okay, so we're going to start at the point 0, 0, go over to 1, 0, and then up to 1, 2, and then back again. So here is our region. And we're going around this way, like that. And oh, by the way, this is not a simply connected, or it's not, sorry, conservative. Not a conservative vector field. Yeah, the way that that's written is a little bit funky. I guess I should just briefly explain. Whenever you have things separated like this, that means that this piece here, that is f of xy is equal to xyi. So that piece there is the x coordinate, if you will. And then the second piece, the x squared y cubed, is the j, the j component of this vector field. And this here, dx and dy, that's just dr. So dr, we're using dx and dy as a stand-in for dr. When you do the dot product of this with dxi, dy, j, then you get that and that. So this is just another way of writing the integral of f dotted with dr. Okay, so getting back to this, let's see if we can identify these 3 lines, because we're going to have to do 3 integrals, but these are nice simple lines. The first one, we have x is equal to t and y is equal to 0. Okay, good enough. Now this next one is x is equal to 1 and y is equal to, wait, what point is that? 1, 2? Y is equal to 2t. So I've just simplified, you know how to write, and by the way, this is, each one of these, we're going to have our t range from 0 to 1. T goes from 0 to 1 here, and then that diagonal line is the only one that takes a little bit more effort or thinking. So that is going to be x is equal to negative t, and y is negative 2t. But once again, you could figure this, wait a minute, no. Sorry, I forgot my starting point, didn't I? There, that's better. So x is 1 minus t, y is 2 minus 2t. But it's pretty much the same. Okay, so let's set this up. 3 separate integrals. So we have the integral of, whoops. Okay, so I need to have my function f is, oh, I've got it up there, xyi plus x squared y cubed j. So let's do the first one. That will be the integral of, sorry, I better write it out, f of r. So this is r1, we'll call it. So this is r1, r2, r3. So f of r1 is going to be, I guess, 0i plus 0j. Well, that makes things simple, doesn't it? Because the dot product, it doesn't even matter what we're dealing with here. You're going to do the dot product. You'll have the integral of 0 dt, which is 0. Okay, so that takes care of r1. What about r2? Okay, so f of r2, that's this. All the hay has to go back, doesn't it? Okay, so this is going to be 2ti plus 8t cubed j. And then r2 prime, I'm just taking the derivative of that stuff up there, is 0i plus 2j. And then I do the dot product of those, and I get, so f dotted with dr is going to be 0 plus 16t to the t to the third. So now I just do the integral from 0 to 1 of 16t cubed dt, which is just 4. It'll be 4t to the fourth. Okay, I'll write it out. Trying to do it quickly. There. Okay, so we're up to 4. So we've got 0 here. This is going to be 0. This one is going to be 4. let's deal with this last curve, that R3. So we got f, no, not little f, got big F of R3. So let's plug in the x and the y for, there it is. This is going to be the worst of the bunch. Do I have enough room? I do not. Let's see, where can I make room? Let me just pull this back. I think if I just write small, I might have enough room. Okay, so f of R3 is x times y plus x squared times y cubed. It's going to be okay. I can do this. Oh, forgot my I and my j. R prime, R3 prime is negative 1i minus 2j. And so f dotted with dr will be negative 2 times 1 minus t squared plus, not minus 2 again, just a sec. Sorry, I'll explain where I'm getting all my numbers in just a minute. 2 times 8 times 1 minus t to the 5th. Okay, so where did I get all that stuff? Well, if you notice, this here is 2 times 1 minus t. So all of this is 2 times 1 minus t squared. So 1 times this gives me negative 2 times 1 minus t squared. That's 1 minus t squared. This is 2 times 1 minus t quantity cubed. So there's my 2 cubed. And I took the 1 minus t cubed and I combined it to make 1 minus t to the 5th. So there's my FDR. Let me clean it up a little bit more. And then I will write down the integral. So I'm doing the integral from 0 to 1 of negative 2. Yeah, let's move the negative 2 out front. Negative 2 times 1 minus t squared plus 8 times 1 minus t to the 5th. How's that? And now this 1 minus t, you could use substitution with it, but why? We can do this in our heads, can't we? If you do u equals 1 minus t, du is negative dt. So if I do the integral of this, just think of this as being one unit, u squared. The integral is u cubed over 3, but because of the negative, I'll have an extra negative. So if you want to do u substitution, go ahead, but I don't need to. I'm going to just put negative 1 minus t cubed over 3. And then this will be 8, 1 minus t to the 6th over 6. And that's another, I need another negative because of the substitution. Evaluated from 0 to 1. Look how convenient. This is going to be, because 1 minus 1 is 0. So I'll have 0 minus, what is this going to be? 1 cubed over 3. So this will be 2/3. Positive because of the double negative, plus 8/6. I have that right? So 0 minus 2 plus 8/3. 8/3 is 4, sorry, 8/6 is 4/3, so this is just 2. Negative 2? Is that right? No? Yeah? Good enough? We're going to find out because we're going to do this using Green's theorem. So my total for all three, we had 0 for the first line, 4 for the second line, negative 2 for the third line. My total for the line integral is 2. Okay, so Green's theorem says that you can do this, you can shorten the whole, look at all the work that we did, so much work. So let's shorten it. And to shorten it, I first of all need to just pull all of this down, copy it, and paste it down here so that we have a comparison. We get rid of some of this stuff. We're not going to do this. We're going to use Green's theorem. Okay, there's, get rid of this. Why won't it just go away quickly? Get rid of that. Okay, good. Good enough. Okay, I've tried. Okay, so Green's theorem. What we're going to do is this thing we're going to call P. This thing we're going to call Q. And so what we're going to do is we're going to do the derivative of Q with respect to Y and subtract off the derivative of p with respect to x. And we're going to do that integral over the entire space. So there's Green's theorem for you. Is you're just going to take this thing. Now, I don't know if you can sort of see how this is going to shake out, but, oh, I've got these backwards. Sorry. Just realized. There it is. This should be dq over dx. There we go. Sorry, because you got to reverse everything, and you got to reverse it twice. So if you think about it, if this were a conservative vector field, if you did the derivative of this with respect to x and did the derivative of this with respect to y and subtracted, you'd get 0. And if you do the double integral over this range, of course, you'd have 0, which makes sense for a conservative vector field. For a conservative vector field, every path that is a loop ends up being 0 because of conservation of whatever it is that you're doing. So if this was energy, gravity, whatever, or think of potential energy, for example. I bike myself down a hill and then I bike back up. Technically, I have the same amount of potential energy. The total energy in the system is the same as when I started. So I go down the hill and maybe on the way down, I gain some potential energy. I gain kinetic energy, lose potential, whatever. You can figure it out. But going down the hill, back up, get back to where I started from, everything zeroes out in a sense. Although I know, I lost some energy through whatever friction, air resistance. But we're pretending that it's like a closed perfect system or whatever. Okay, so here's what we'll do is we just have to figure out the derivatives of these things, and then we're all done for the day. We're going to do the derivative of q with respect to x. That's easy, 2xy cubed. Subtract off the derivative of p with respect to y. That's easy enough. I have my region here. That's easy. I'm going to use a vertical rectangle, which means that my x's will go from 0 to 1. My y's will go from 0 to y is equal to 2x, because that line there is y equals 2x. So let's see if we can pound through this in the next minute, which I think we can. So this is going to be xy to the 4th over 2 minus xy, evaluated from y equals 0 to y equals 2x. So let's see, 0 to 1 of, let's see, what do we got here? 2x to the 4th is 16. So this will be 8x to the 5th minus, what's that going to be, 2x squared? I think I got that right. So you plug it in yourselves. I'm plugging 2x into here, 16x to the 4th, but then I canceled and combined. No one's complaining, so we'll just go on. And then this becomes 8x to the 6th over 6 minus 2x to the 3rd over 3, evaluated from 0 to 1. And I think you probably can see what's about to happen. So we have 2, that's 4/3. Oh, wait a minute. That's not right. That's not the same thing. What did I do wrong? Do I have a negative out of place? Hold on a minute. Do I have a negative out of place? It should come out exactly the same, because it should be exactly this. No, that's right. This is right. I must have made a mistake somewhere, because it should come out exactly the same. Let me see. Do I have my formulas right? I do. Strange. I'll have to double check. Well, it's a good thing that we aren't going to have any homework over the weekend, except for a couple of very important things. I think there's like playing board games and going on hikes. Look on the assignment sheet. Make sure you fulfill, oh yeah, helping your parents or whoever you're with, doing dishes or what have you. That's your homework. So I'll double check this. I won't bore you with my checking now. And then we'll reconvene. No homework other than doing those fun things over the next few days. So we'll see you on Monday. Stop.